So, we identified these basic optimizations that a multi-level logic minimizer would perform, and our objective is that due to the encoding that we select, we somehow enhance the availability of these opportunities to the multi-level logic optimizer. And again, the target here is multi-level logic, and some of the arguments that are made later have this in mind. For example, if the target were different, if it were two-level logic, then the arguments would not hold, the specific arguments would not hold. Okay, let us go through some of the basic ideas of this particular strategy. This is a strategy that we are studying in more detail, primarily because there are some ideas there that are generic enough that help us formulate the problem, that help us also understand the relationship between what happens at an early stage problem and its solution, such as this one, and its interconnection with later stage strategy, later step of logic minimization. Happens later, ideally one should be aware of what goes on there at the time that we make decisions here, but due to the sequential nature of the flow, we have to make certain assumptions. Rather than running logic optimization at this stage, we make certain assumptions and estimations about what will happen later. Okay, let us study in a little more detail some patterns that we can identify in the state machine that is given to us, and in terms of that we would formulate the solution to the encoding problem. So, this is this state machine that is given. The table is an alternative way of representing it, and what we are pointing out here is a couple of rows, this one and this one. Okay, that corresponds to a subset of the FSM that looks like that. You have a common next state with two different present states, S0 and S2, right. That is the state diagram, part of the state diagram. So, that is the pattern that we have identified. There is a common next state S1 and two different present states S0 and S2. These are of course the inputs, x and y are the inputs to the FSM. So, they show up here. That is the condition under which you would make the transition from state S0 to state S1. And what you have here is the output. There is a single output here Z, and here that output is do not care, but here that output is 1. So, this is of course an equivalent representation of just those two rows, each row corresponding to an edge in the FSM, a state transition. So, we identified this pattern on the basis that there is a common next state and there are two different present states. What is the implication of this? Let us study by going all the way to the Boolean expressions and visualizing what the gate structure might be that would help us implement this ultimately. Now, if I take this state table and do an encoding, let us use this encoding here using 5 bits just for illustration. Number of bits of course is an orthogonal decision, and you can assume that maybe what we have identified here is only part of the FSM. There may be many other states. That is why we are using a 5-bit encoding for the FSM states. So, let us assume this kind of an example encoding is made. That is the encoding for S0, that is the encoding for S1, that is the encoding for S2. And when you do that encoding, what you end up with is a state table is converted into a truth table that looks like this. Wherever you have S0, that gets replaced by the encoding for S0, that is the encoding, right. So, that gets replaced there. S1 is replaced by this and S2 is replaced by this. So, this truth table of course is a function of what encodings we have chosen for the individual states. Any questions on this? This is an elementary implication of an example encoding that we would perform. Now, let us study what happens as a result of the encoding. Of course, the state table is converted into a truth table. That means that all the states, the symbolic states we have here, are assigned their respective encodings, and we have a truth table here. Okay. Let us continue to the Boolean expressions that would implement the truth table. So, the truth table has these on the output, right. This is the input section and that is the output section of the truth table. These outputs are correspond to what? The next state. So, those are essentially these A, B, C, D, E values. So, we are trying to build the combinational logic for this. Part of that logic is the output, that is this one, and the rest of the output here essentially is going into the state register. So, the truth table of course captures both of these outputs. One is the next state signals, the other is the output signals of the FSM. So, let us build the logic. I have to build an expression for all of these 6 outputs, right. One for A. Yeah, question.
So, the state register will be giving the previous present state, na? And the combination logic output will give the next state.
Right.
So, small ABCD should be after the state register, capital ABCD should be before the state register.
These are my outputs from the combinational logic, right. So, these are the D inputs of the flip flop, those are the Q outputs of the flip flops. Yeah, I did not draw the direction of the arrows, but that is what it is. Yeah. So, capital A, B, C, D, E are the outputs of the combinational logic, they feed into the state register. Okay. So, now what I need to do is for each of these columns, output columns, I need to pick up all of those rows where that output is 1 and build the expression, or the other way around. I can pick up all those rows where it is 0 and build an expression and invert it, either way both are equivalent. So, let us just take all the ones that are there and form the logic. So, A will be equal to this expression, where does this come from? Plus this. So, there are 2 expressions there, 2 terms in the expression for A. Where do they come from and why do we have these 2? One should correspond to that, one of these terms should correspond to that row, being 1 for A, which means that we will pick up the corresponding input here. First, let us look at the xy. So, xy is 0 1, so that is my x prime y. A, B, C, D, E, we had S0 there, this is the encoding for S0. So, I have B prime C prime and A, D, E, that is the expression. So, that is what I have here. So, that is my expression corresponding to these inputs. Okay. Then the other one would correspond to picking up that expression, that is what I have there. For B, what would I have? It is the same as this, as the, why is it the same? The expressions for A and B are identical so far. Why are they identical?
Because both A and B are 1 together.
Both are 1 together, at least as far as these 2 rows are concerned, they are indistinguishable. So, it should be the same expression. Same for C. D and E, I have nothing here. Why do I have nothing? Because these are zeros, right. So, my strategy was that in building up this Boolean expression, I will pick up all of those rows where that output is 1, right. So, where it is 0, I just ignore it. At least these 2 rows do not contribute anything to D and E. What about Z? Z is also an output, so I have to build the logic for Z. For Z, I have 1, but the other one I do not have anything. what I have here is a do not care. Do not care of course means that you could treat it as one or the other. For now let us just leave that if it is do not care, which means that you treat do not care as a 0. That is just for illustration purposes. We do not of course actually treat do not care as a 0, but this is essentially what is corresponding to the second row, same input conditions. Right. So, that is how I would build up my Boolean expressions for implementing A, B, C, D, E and Z, all the outputs. So, that is the logic that that combinational logic block is supposed to implement. Of course, as of now I have only specified very explicitly what those expressions are. This is not an optimized form of that expression, but it is just like the specification of a Boolean function. So, that we start from here. Any questions about the way we form this? This is of course an important first step in any further arguments that we make. Those were my set of expressions, and let us get to identifying optimization opportunities in those expressions. Optimization opportunities for us right now are the process of identifying common cubes, because we said that that is what we can concentrate on. It is easier than finding general common sub expressions. Common cubes, if I look at that expression for A, I see that there is a common cube between that expression and this expression. That common cube is this much, A B prime E. So, these two expressions are different in terms of some of the variables, but they are common in terms of some of the other variables. We are just trying to find out which ones they are common in terms of, and for now let us just restrict our attention to the state part of it, A B C D E part of it, okay, not to the x y. They can be treated similarly, but since this argument is about states, let us focus on the A B C D E. So, C and D are different in these two expressions in terms of their appearance as normal form or complemented form, but A, B and E are the same. So, I can extract that portion that is highlighted in green as a common cube, and then I can express my A in terms of that common cube. You can see that this will lead us towards a better implementation, at least in terms of gate size, gate count. It should be better because I have extracted that common cube. I do not have to do that repeated ANDing. Instead, I have done that ANDing only once, and that output S can be sent to various other expressions as we compose the multi-level logic implementation. How did that happen though? That common cube arose because of what? Remember, that part was in the state table, it was just a symbolic mention of S0 or S1 and S2, that is what it was. So, what is it that caused the appearance of a common cube? This was not part of the original specification. It is the choice of the encoding. Remember, we have a choice. This is an example encoding that we have taken, and due to that we could extract some common cube. There are two aspects. One is the size of the common cube, that size is 3 literals here. Other is the number of appearances of that common cube. Both of them somehow influence the total area of the ultimate implementation. Okay. So, it is that encoding, and if there was a common cube of size 3, it is due to what property of that encoding?
That 3 states were there, and it could be encoded in 2 bits, whereas we were using 5 bits where 3 bits are redundant.
Oh, remember, what we have here is only part of a bigger FSM. It is certainly possible that I have 25 states in the FSM, and I would choose 5 bits in that case. So, the 5 was chosen just to illustrate the point, it does not have to be 5, but even if it is a minimal encoding, right, then too you will find common cubes. The appearance of the common cube does not necessarily follow because of any redundancy in the encoding.
So the common next state is the theme. So you would prefer to maximize the uh, align the number of or rather when you have common states next state, then make sure that the number of transition in the bits in the input states is minimum, so that we can extract the maximum cubes.
Why did we have a common cube of size 3 in this example?
The Hamming distance was 2.
Between Hamming distance between which two states?
Different input
The
and gave
two
common outputs.
Yeah, the original state. So S1 is the next state. So between the two present states S0 and S2, there was a Hamming distance of 2. Therefore, the other 3 bits were the same, and that is what led to the appearance of a common cube of size 3. There is nothing sacrosanct about that size 3 though. If I wanted, I could have got a size 4. How would I have got a size 4?
Just need to change either of
Changing the encoding of S0 and S2 in a way that they are distant by 1 unit. Could I have had a common cube of size 5?
No.
For those states I can't, because that would violate the requirement that states of course be distinct in their encoding. So that is what it is, that the size 3 appears because of the choice of encoding, our choice, and from the fact that Hamming distance between those two encodings is 2, we can infer that the lines for A, B, C, all of them will have a common cube of size whatever is the max. So here the max is 5 minus 2, that is where the size 3 comes from. Okay. While this was the argument for the next state, a similar argument can also be made for the outputs. There is no difference, right? These are also outputs, the capital A, B, C are also outputs, the Z is also an output there. So why did we go through this argument? It helps us formalize at least something. Intuitively, what does it tell us? I can look for such occurrences of patterns in the finite state machine, and if I find such occurrences, then what do? There are some things that I can't fix, there are some things that I can fix, that is up to me. What I can't fix is the structure of the finite state machine, right, that is given to me, but what can I fix? The choice of the encoding is up to me, and if it happened that this is all that was there, or I find patterns like these, then I can informally try to do what in terms of the encoding? Try to keep these two states S0 and S2 as close as I can. That is really the intuition. There is the next step of how to quantify that intuition in some formal way, but the idea is this informally, that we are looking for some patterns, and we already know that if those patterns exist, then there are some implications with respect to possible optimization opportunities for the logic minimizer later on, and what we have in our hands is the encoding, and we can do something about the assignment of the encoding. Yes.
Typically, when we code FSM, while writing even RTLs, it is advised to keep the states as enums, in the sense so that your RTL is readable.
Yes.
Right. So that means encoding is even done at a gate level synthesis, where it's RTL to
Encoding
is part
is
of
a more general problem. This is being introduced here with respect to a finite state machine, but as you can see, all this logic in fact has nothing to do with the finite state machine. This is a truth table. There is a process of symbolically translating that FSM into a concrete truth table. The idea of encoding is of course more general. You could have encoding being defined for just combinational logic, even if you did not have anything sequential, even if you did not have a finite state machine, but you just have had an input and an output. You have a truth table, but in fact you can, for the purpose of minimizing logic, take some of those inputs and encode them as some other values if it helps in some way the final logic that is being generated. You could imagine conceptually an encoder at the input stage, a decoder at the output stage, and the intermediate logic is what you are trying to optimize. Maybe it makes sense to do such an encoding and a decoding.
So how do we know that we have to encode with n number of bits?
That is a separate argument. So, we went through that, right, initially, even before deciding on the encoding, you have to decide the number of bits, and we did talk about the two extremes. One is if you use minimum number of bits, then what is the implication? If you have a one hot kind of encoding, then what happens?
But here if we estimate the number of states, and according to that, it doesn't come under hot encoding, because the number of states are 3, then
No, the number of states in that table is, this is just 2 rows of that table. The table can be much bigger, maybe there are 25 states in that table. That is why you have 5 bits. Okay. So, it is a different reason. This argument holds irrespective of what is the width of the encoding. I made it 5 just to illustrate the effect, but what I have here n minus h, that is the one that is a general argument. It applies for any n and any h.
So for large FSMs,
Yeah.
I mean, because it's used even today at logic optimization in RTL to gate level, this could become very intractable.
No, we absolutely want a practical solution to this. I haven't indicated an algorithm.
Right, but I am just
What do
wondering
you mean
how
it will become intractable, since I didn't tell you what the algorithm is? So, we are still in step 0 of the algorithm, where we are saying that if such a pattern was there, then you could do something about it. That is just one of the arguments. Let us look at it the other way around. Identify a pattern where you have 2 transitions with a common present state. That is these 2 rows that leads to a structure like that. S1 is the common present state, S0 and S2 are the common next states. For that example encoding there, the corresponding to truth table rows will be something like this, right. S1 is encoded into this, S0 is encoded here, S2 is encoded here. That is the encoding. What optimization possibilities we see there? Let us go through the same process of generating the Boolean expressions. So, from this I again construct the expressions for A, B, C, D, E, Z, all of these. The expression for A has what terms? It has this term and this term. Expression for B has nothing. Again, of course, that is because of the choice of the encoding, both are zeros. For C, so these are 2 different states, right. So, the encodings are different, 0 in one case and 1 in the other. So, I would pick up the expression corresponding to that row. For D, similarly, I would pick up the expression corresponding to this row. For E, I would have the same thing that I had for A. Similarly, for Z, I would pick up the same thing that I had for C. So, I have this set of expressions. What can we say about the availability of common cubes in this set of expressions? The transitions depend on the inputs. This is a common present state, of course. So, if I look at these 2 expressions, in fact, focusing our attention on A, B, C, D, E only, this entire expression is common. Why is it common? Is it because of anything we did in the encoding? No. Why is it common? Well, common for all the 5. because it is the same present state, does not matter what the encoding I had given, that is going to be common. That is because of the pattern that I am looking for, that since it is the present state is common, I would have a common cube of size 5 no matter what the encoding. So, generalizing, if I had n bits, then if the Hamming distance between the two next states S0 and S2, if that was h, then what can I say now about the availability of common cubes? So, I was able to extract this out, that is good, its size is even bigger, it is a size n common cube. It occurs in some places. If you look at the individual expressions for the outputs, some of them it certainly occurs for A, it occurs for E, does not occur for B. Also within the C's expression and D's expression we did not find it, but we did find it within A's expression and E's expression. So, what is that attributed to? Some of the next state lines would have a common cube of size n or size 5, that is what it is. How many would they be? So, two things we are looking for, one is the size of the common cube, other is number of occurrences of the common cube. Size is 5 in this case, this is not dependent on the encoding, but what about the number of occurrences? Viewed independently, view the logic for A independently, logic for B independently and so on. There is an opportunity for A, there is an opportunity at E, but there is no opportunity here for B, C, D. This happened because of what, and in general how many next state lines out of the 5 next state lines we expect a common cube in.
The number of ones in the next state.
Including
The number of ones, my question is, view this logic differently, all of these logics differently, logic for A differently, logic for B. For each of them we would like to identify, is there a common cube of size 5. So, for A it is there, but for B it is not there. For C also, C and D also it is not there. Within the logic of C and D it is not there, but for E it is there. So, how can I characterize the number of appearances of the common cube within the respective expressions?
Somehow same as having this.
Distance between repetition of basically repetition of my present state. So with this input combination, these are my present states, and with next input combination, these are my present states. So whenever my present
This is a pattern in which the present state is common.
yes,
So, in both the rows the present state is the same, what is different is the next state.
yes,
So the
see
inputs,
from the A to E, this is common, like from the ABCD in the first and the second, there is 1 1 in the same line.
There is 1 1, right. So, how do I in general characterize it? Number of common cubes that would be there.
for the
Number of
same
common
present
bits.
state, the number of inputs that will change will define it. That
Yeah,
will
yeah. So, this pattern is the same present state. Same present state is leading to a common cube of size 5. Right. But what is leading to the appearance of 2 common cubes? The distance between present and next states.
number of inputs.
What difference it makes, the distance between present and next states? Somehow something that is the same between A and E, right? What is the same?
so the A, B is same and E is same, and only 2 bits are changing. So somehow that 2 is still related to it. I can't explain it in why.
It has to do with the way we are encoding the next states. These 2 states have something in common that is showing up in those expressions there. What do they have in common? See, S1, it does not matter what you assign, that is showing up here, right. And we are saying anyway that is the expression, does not matter what the encoding of S1 is, you will find a common cube of size 5. And what that actual value is, A, B, C, D prime, A prime, that is derived from the 1 1 1 0 0 that was chosen for S1. If you had chosen a different encoding for S1, you still have a common cube of size 5, but that expression would be different.
One quick question.
Yeah.
One quick question. It will add some clarity, I hope. So in previous case, we are looking at vertical common cube, right? Here, are we looking for horizontal common cube?
Well, why don't we look at these arguments are subtly different. They are not exactly the same. We are looking for a common cube here within the expressions, right? But actually, the previous one was also not very different. Here too, we were looking that it exists across the lines is a different matter, but there too the common cube did exist.
But here we are
for the
looking at
output line.
horizontal at least. That is the
For the handling distance between input patterns.
So why did we have two? First of all, where the bit positions at which the bits are different corresponding to S0 and S2, those correspond to the C and D, where anyway there is no common cube. Right. So we are restricted to the other three positions that are actually common between the two encodings. Now, but even in those three, it turns out that one of them is a 0 and that does not contribute to a common expression there, because we are actually ignoring it. So, the common part is 1 0 1, that is A, B and E, but since B is a 0, then it does not really contribute towards anything. What is actually contributing is that part that is common between the two next states encodings that actually have a 1 in them. So, what is common between S0 and S2? It is that 1 0, these things are not common, and a 1, right. What is highlighted in pink, that is what is common between S0 and S2. You can see that the expression for A, so these are of course A, B and E. This commonality is showing up in these expressions that we have built. This being 1 in both the cases is actually showing up in that expression, that S repeating here. Similarly, this being 1 in both of these cases, S0 and S1, that is showing up in the S repeating here. The C and D not being common is showing up in those expressions not repeating there. The D had a potential to be common. If we had encoded this as a 1, then that would show up here, a common cube would show up, but actually since it is a 0, we are not even picking anything. So, there is nothing here. So, first I can identify the Hamming distance between them and get my n minus h. So, these are the three potential lines where a common cube could exist, but at the lines where it will actually exist would depend on which ones I have given a 1 there. The ones that I have given a 0, those will not show up. That is what the logic is. This is in some ways a different argument from that common next state logic, that is why we went through it separately. Okay, so these are my patterns. For an FSM, we can identify many such relationships. So, this is just 2 rows that we just looked at out of a bigger FSM, and I can use whatever algorithm to traverse the FSM and look for patterns like this, either common present state or common next state. And through it and quantify in some way the distance of the codes versus the size of the common cubes and the number of the common cubes that I exist. This is what we have in our hands. The encoding can be made in a way that the distance is minimized or maximized, in a way that the size or the number of common cubes, the availability of those is maximized. So, the strategy would be as follows: you try to estimate the reduction in the literals, that is what we call the gain, if 2 states are assigned close codes. Both of those patterns that we identified, in the process we inferred that a particular pair of states should have close codes. That is informally what we want, and there is a little bit of a detailed quantification of how do you prioritize them, which is higher priority, which is lower priority. That priority is identified first, and then we will come up with a strategy that takes that priority into consideration. But you estimate that reduction if two states are assigned closed codes, and by identifying those common next states or common present states, we can try and put numbers there saying there is a greater chance of literals being reduced if these two states were close. So that when there is a competition for the actual encodings, priority can be given to making those particular pairs close that are more worth it with respect to how we have estimated the reduction in literals. So, I would like to assign codes that maximize the number or the size of the common cubes, and of course, the encoding process stops there. You assume that once those common cubes are available, the subsequent logic optimizing step will find and exploit those common cubes in the way that you expect it to. This is a basic requirement of any logic optimization tool. You do not want to probably put too many dependencies between this higher step and the next step, because then it becomes tool specific what you do here. But the idea of identifying a common cube and exploiting it is something that is basic enough a requirement of a logic optimizer, that it should work irrespective of which particular logic optimization algorithm is being used. While that was the informal intuition, this has to be formalized in some way, this has to be quantified so that we can make a decision in the encoding. You build an undirected graph where the nodes correspond to the states, and the edge weight is the gain if those two states are assigned close codes. So, that is the number that we will compute, and we will put a number on each of those edge weights, and the higher number, which means that it is more gain is there if they were close in their encoding. And you at the end, after the graph is formed, in a second stage you assign the encoding that maximizes the total gain. So, there are two parts in the formulation. First is building that graph itself, and the second is once you have the graph, solving that graph in terms of an encoding that would maximize a cost function in some way, and that cost function here is the total gain for all the encodings together. Okay, so let us look at the building of that graph itself. Fan out just corresponds to one of those strategies. There is a different strategy that is also covered in the paper called fan in. We will look at one of them in detail. Idea of course is what we already said, if there are two present states with the same next state, and output of course is there, and they will get high weights, which means the edge connecting them. This is the graph that is being constructed. So, that edge will have high if we can find the pattern. So, for example, that common next state pattern is there, right. So, if that common next state pattern is there, what is the logic? Logic is that S0 and S2, if they were minimally distant, then I would maximize the appearance of those common cubes somewhere. So, the priority can be high. So, high priority here in terms of a higher annotated number, this is an estimated gain for literals, that would lead to closed codes eventually. The second stage of the algorithm will make sure of that, and essentially what it represents is that the size of the common cube is maximized. So, if I have something like this, if this situation arises from the state table that I started off with, then maybe in the later stage I choose an encoding like this, where there is a large common part in the encodings I select for S0 and S2.
If I have multiple such common states,
Yeah.
there can be a scenario where the priority of making two states same is same, right? So, the gain I get.
So, that shows up in the quantification. There is a graph that is being built and a quantification being made for every pair of states. Some of those edge weights ultimately might turn out to be equal. We will quickly go through this quantification just giving the basic logic for doing so. You could quantify it in some other ways also, but let us go through the same logic that is that's proposed by the authors of that paper. You construct some output sets. If you had 3 outputs here, you would construct 3 sets. So, the Z corresponds to the output, there is only one output here. So, we construct one of the sets in the following way. If 2 present states assert the same output, then a common cube can be extracted for reasons that we saw earlier. You construct NO if there were O outputs, different output sets. Here O is equal to 1, so you are constructing only one set. So, what you pick up is this: all of these present states that assert that output, means which lead to that output being 1, those are what we are picking up. Okay. So, S1 is one of those states that lead to an output of 1, S2 is one of those states, and S3 is one of those states. We not only keep those elements, but we also include the number of appearances of S1, number of appearances of S2, and number of appearances of S3. So, we are also counting the number of times that present state occurs. Why is that number essential? So, it is used later on. Essentially, the more the number of times that present state is occurring, the more the number of occurrences of that present state when you actually form the logic. Because remember, at least at the first step, we are picking up that Boolean expression, this Boolean expression, every row we are picking up that expression, right. So, that many times that expression will occur, and some weight we are giving to present states that occur more number of times.
So, on previous slide, just one.
Yeah.
Should we also assess? In this case, we have only one output. It's a very simple case, but still, in this case, would it be faster for us to build a logic with 0 output and then negate it as necessary?
It could certainly be. Through all these illustrations, we are making one assumption or the other, but everything that we are saying could well be inverted, and you could consider the zeros at the different stages and build an inverter out of it, and ultimately whatever the output is taken, that is inverted. The logic might still be the same. Here we are not taking that decision though, because remember, this is a high level argument, the actual logic optimizer is not yet there. You expect the logic optimizer to indeed evaluate the two and make the selection that is better.
Even during encoding, if I, let's say in this state table, I had only 2 zeros.
You could, this is an illustration only, and all of this could well also be. For example, note that the don't care is not resolved by us, and at some point we just randomly assumed that it is it translates to 0, need not, it could also be 1 and so on. But the logic could also be used by looking at it the other way around and taking the inversion. You could still reuse the same logic, but choose the zeros, the complementary part of it instead. Okay. So, that corresponded to the output. Now, let us look at the other part of the output, which is the next state logic. Our idea was that if 2 present states produce the same next state, then a common cube can be extracted. That corresponds to the intersection of the 2 present state encodings. That was our first pattern. How many common cubes are there? So, that corresponds to the number of ones in the next state encoding. That I do not know yet, because the actual encoding will happen later. But still a quantification has to be made, and the way that is approximated is, assume that half the bits are going to be 1, where NB is the size of the state register, number of bits that you are choosing, if that is NB. In our example there, NB was 5, width was 5. Assume that half of those bits are going to be 1, the other half are going to be 0. and that is something that will help us in the quantification. How many cubes are there? Two things are there, right? One is the size of the cube, other is number of occurrences of that cube. Okay. So, now you construct n s different next state sets. So, one for every state. Okay. In each of them you capture those states which are present states with this S0 being the next state. Okay, that is what is the next state set. So, what is highlighted here in green are those rows where S0 is the next state, and we are constructing this set corresponding to S0 being the next state, and we are capturing here those present states that lead to S0 as the next state. Notice that S0 is there as the present state, and that is all right, that does not change this argument in any way. If it occurs both as the next state and the present state, our argument is still the same, which is that there is a cause for S0 and S1 to be close in terms of encoding, irrespective of the fact that it occurs on the next state also. This was an argument that related the two present states. So, that is still there, it does not matter that one of them is also the next state. Fine, that is my next state set construction for S0. I can build the same thing for S1, S2, S3 and so on. I also annotate here the number of occurrences of each of those states in the present state. So, 2 occurrences of S0 and 1 occurrence of S1, that is what those numbers are. Okay, so, I can build this for all my states. Now, I have to build my graph. I have captured so far this much. One was an output set corresponding to every output. I would have those sets. If there were 3 outputs, I would have 3 sets. Then I have these next state sets. There would be one corresponding to every state. Well, every state that matches that pattern of common next state. Okay. Then I have to annotate the edge weights. It is a fully connected graph. If that pattern never occurs, then it is fine, you just have a 0 there on the edge weight. Right. So, here is what we are doing in the process of constructing those edge weights. Let us say S2, S3 is the pair, that is the edge that we want to build the weight for. You look for sets in which S2 and S3 both occur together. All of these are providing some argument for S2 and S3 to be close codes, remember. So, because this is the common next state, that is a common next state, and this is a common output. All of them have this property in common that they are setting up an argument for making S2 and S3 close. Now, of course, there is competition. Now, if you look at S0 and S1, similarly another set of pairs could be chosen. This is such an example, S0 and S1, this is also such an example, and so on. So, since these pairs occur a number of times, we ought to prioritize them in some way, and that is the quantification that we are trying to build. Notice that S0 and S3 never occur together in any of these sets. That is why that number is 0 there, telling us that it is not particularly important that S0 and S3 be close in any way. They can be least in terms of the priorities when we choose the encoding. So, the way the quantification is done is we multiply these numbers. We consider this a pair at a time. We multiply these two, we also multiply these two numbers. That is what leads to that 3 times 2 there. The 1 times 1 comes from here, the other 1 times 1 that comes from there. This is scaled by NB by 2, that just corresponds to the number of ones in the encoding for that state. That many times you would have that common cube occurring, but actually I do not know how many ones are there. The ones and zeros I still do not know. We are still only right now arguing about higher priority and lower priority, right. The ones and zeros will be assigned later. So, I do not know how many of them. So, I will just multiply this by NB by 2, assuming that half the bits are 1 and the other half are 0. Wherever you have a 1, you will have an appearance of that common cube. You see that the argument is the same even if you had picked up the zeros, because the number of zeros are also the same. So, that is the scaling that I have there, and I ultimately come up with some number 8 that gives an estimate of how many literals I would save if these two were S2 and S3 were close. Okay.
So the significance of half is not very clear till this undirected graph. Maybe later it's there. The NB
Why half?
The NB by 2, the scale
Right,
NB
right,
by
right. Why did we multiply this by
benefit
n?
out of it, not exactly.
See, what are we trying to capture here? So, there is something that is quantified, right. What I want to estimate is the number of times that will occur. The number of times that will occur we can look at by, maybe we can go back to our common next state argument, right. We said that in this case there was the possibility of a common cube of size 3. Why 3? 3 corresponded to what was common between S0 and S2, that we are not directly controlling. This will be the output of our encoding. But there is a other thing, that this is occurring in A, B, C, but it is not occurring in D and E. Why is that? A common cube of size 3 is occurring for some of those expressions, but it is not occurring for the other expressions. Why is it not occurring for the other expressions? Because if I look at the encoding for the next state, there is a 0 for D and E. That is why I did not have these. Now, the question is, I want to do two things. First is, how much is there in common? That is the size of the common cube. Other is, how many times is that common cube occurring? Okay, so, the scaling that I am doing is with the number of times that I expect that common cube to occur. That is the reason for the multiplication. Now, this is a tricky question because I do not know how many, there were 3 occurrences here just because of my choice of 1 1 1 0 0. If that encoding was different, then the number of occurrences would be different. Okay. Now, I do not know the encoding right now. At this stage I do not know encoding, right. Encoding is going to come later in a separate step, but I do need to multiply it just to give a little more authenticity, be more precise. So, what I am saying is I will multiply that whatever my estimate is by 5 by 2. Here in this particular case it should have been 3, but that would be as a result of the choice, but that choice is not yet there. But this is kind of an estimate of the number of times that common cube is going to occur. That is my NB by 2.
What I meant was all the edges are getting multiplied by divide by 2. So it's a relative change. Even if we don't do it, would my relative priority change?
No, no. There are two components of this quantification. One is this. The other is the output. That is not being scaled.
Okay, that is
Right. So there is a difference between the two. You are right that if everything was being multiplied by 2, then why have the 2? I could remove it.
Oh, I didn't notice. Sorry, my mistake.
Okay. So that is my graph. The paper does mention a different algorithm called fan-in. This was essentially taking the common next state argument and quantifying it. There is a different argument which is along the same lines, but I am skipping that, called fan in. That would essentially take care of the other argument of a common present state, and similarly build an argument and build an undirected graph. You get in general different graphs for fan in and for fan out. You could pick either of them for the encoding, but the objective at this stage is to come up with the graph. That graph somehow captures an important property that helps us later in the encoding. It tells us that if that number is high, if that edge weight is high, then it is higher priority. Addressing that pair is higher priority in terms of the encoding. If that number is low, then the priority is low.
So one more question.
Yeah.
Here the outputs were fixed 0 and 1. Somewhere a decision has happened that my output has to be 0 or 1. But typically when we are designing the architecture and things, we have flexibility of deciding the output states also when two FSMs are going to interact. Like when I am partitioning the bigger design into smaller design, I have flexibility of changing the output bit definitions also. It's up to me.
Yeah, in fact, even here in our context of HLS, where did the FSM come from? This is the output of the HLS step, right? Do we have a choice with respect to these outputs? What are these outputs anyway from the FSM? Where are they going? They are going into the data path. They become what in the data path?
Control signal.
The control signals, particularly the select signals of the multiplexers. Do we have a choice of
Yes.
making it 1 or 0?
Yes.
What is the implication of choosing 1 or
Register
0?
swap.
Yeah, it just reorders the inputs in a different way. Certainly we have the flexibility to reorder the input. So you could in fact, just like the symbolic states, you could have the outputs also being symbolic.
Divide by 2 for output set also in that case. Just to confirm.
Yeah, you anyway, if once you have symbolic, you could do the similar argument for.
I wanted to confirm that part, my
yeah,
understanding.
of course, the FSM synthesis is taking the FSM in a general manner. That you have the flexibility to encode or not is a different question, and it turns out that in our context, as in many other contexts, you do have the flexibility, but after all, a finite state machine, there is a formal definition of what a finite state machine is, and this algorithm of course is targeting that formal definition where explicitly you have ones and zeros and don't care on the inputs and outputs. Okay. So, the second part would be what is called a graph embedding problem. You start with that graph that you constructed and you want to assign codes to each of those states in a way that the total cost is minimized somehow. What is the cost? We can easily use the Hamming distance of the encoded state along with the weights that we have assigned here in this graph to come up with a cost in this way. So, sum over all the edges that you have in that graph, the product of these two things, one is the weight, right. If it is 2, then that is the weight, and the 2 is multiplied, the weight is multiplied by the Hamming distance between those two states. You can see that if the weight is high, then to minimize the cost, it is worth keeping a low Hamming distance, and if that weight is small, like the weight is 0, then it does not matter, you can keep a high Hamming distance. So, that would be the cost function that we would like to minimize in such a graph embedding problem. We can easily motivate it using 2 random encodings. Say you select one of these. So, that is a valid encoding. 2 bits are being used and of course, they are distinct. So, that is one valid encoding. The cost can be computed like this, the sum over all the edges, you get a number like 27. Of course, the reason this was chosen in this way is that you have an expensive encoding for that particular edge that had a high, the transition that had a high edge weight, right. Intuitively, what should we be doing in terms of this encoding? Since this weight is high, we should be assigning codes to S1 and S2 that are minimally distant, but this encoding is not doing that. That is all. So, the weight is relatively high. If you choose a different encoding, particularly make the distance between S1 and S2 small, then you go through the same things, you will end up with a lower total cost. So, the graph embedding problem is to select encodings in such a way that that cost is minimized.
The weight of edges were the gain factor.
Yes.
So that gain we have no control over after we have reached this state.
Yeah, we are assuming that this is fixed now. The graph is given, and once the graph is given, then it is actually a graph problem. It represents our synthesis being modeled in this way, but graph embedding indeed is a more general problem, just like graph coloring, that we were able to translate it into such a known problem, and we can solve it using one of the algorithms that is available.
The gain is a function of the input graph, that's the state tables that are
Of the
on
state
it.
tables.
We don't have control over gain.
Encoding.
We do not have a control over the gain. Well, we did control it in the sense that it is the output of our quantification. Where did those numbers come from? We made that calculation, right, for the Fanout algorithm. We said that this is how I will calculate, and we put those numbers there. So,
It is a fixed thing. I mean, you don't
it is fixed, but we chose that particular strategy to quantify. There is nothing sacrosanct. What is fixed is the structure of the FSM, that is fixed. Now, from there we said that if you have common, if you try to extract common next states and so on, then you quantify in this way. In fact, an alternative algorithm is also there for the fan in, which would actually result in a different graph for that same FSM. That is where there is the possibility to play around a little bit in terms of what you want to prioritize.
Till that point we are trying to minimize the gain factor between edges.
Yeah.
And
Yeah.
Once we are done through that phase, then the gain is fixed. Then here we are trying to fix the heavy
Yeah,
distance.
assuming that the gains are all somehow nicely captured in that graph, now the problem is just to find the encodings.
Hamming
Right,
distances
right,
that will be minimum
right.
at highest gain.
Right. In fact, the way this problem is formulated, you can see that, it is not clear if you can see that, but there may be many solutions. If you can find one solution, you can find other solutions too that have the same cost. Is that clear? Why is it so clear? Or is it not
Sir,
clear?
we have found one solution for the cost.
Right. Suppose you find one solution that minimizes the cost. You can argue that you can find other solutions for the same cost.
Different encoding.
Yeah. What is the guarantee that you can find?
So 101 and 110 again. If they are the same hanging distance, it will give the
Right.
same cost.
If all the encodings were inverted, you would have the same. The argument here is only in terms of the Hamming distance, not in terms of the absolute code that you are assigning, and therefore the problem will admit multiple solutions. Okay, why encode the problem in this way in terms of the graph embedding problem? This is another one of those well studied problems, so you do not have to work out the solution. Difficult, it belongs to that class of difficult problem. You can see that a large number of choices are there, exponentially large number of choices are there. However, the heuristic that we choose can be related to some property that we expect for these graphs. These are not just general numbers that we expect on those edge weights, but there could be some expectation, particularly when you have large FSMs. The practical observation here is that you expect clusters of nodes with high edge weight. All the edge weights are unlikely to be balanced. This is just the nature of the kind of FSMs that practical FSMs that we have. You could in theory construct an FSM that gives any graph there, but practical FSMs have this what property, that even if you have 100 states in your FSM, having 100 states is not impractical. You could have hundreds of states, but they are not all densely connected to each other. All the states are not densely connected to each other. It is sparse in terms of the transitions that you find, even if the number of nodes is large. There could be n square transitions in the worst case, but you do not find n square transitions for practical designs. So, it is sparsely populated, right. That would lead to even that graph also being sparsely populated in terms of non-zero edge weights that you can expect. So, clusters of nodes with high edge weights are expected in that graph that could be used to guide our heuristic in some way. So, the heuristic decides in what order to choose the nodes for assignment, because if you choose one order, there are a number of encodings that are not available for the nodes that come later in that order. So, somehow you are prioritizing those nodes. And our strategy then is you identify the heavy clusters and assign codes to their states of those clusters first. Heavy means what? Priority is high, that is why the cluster became heavy. Then I just remove those states from that graph and I just proceed encoding the remaining graph. That is all that I do.
Can't we delete all the zero weighted edges? Don't form those. Delete
Well, yeah, it is the same thing.
Yeah.
Yeah, not very different. It is an implementation thing. For efficiency purposes, you could remove those
Cluster of
weights.
nodes as in many nodes which are densely connected. We are optimizing them
Right.
first.
This is only an informal notion. So, this has to be formally identified. What do you mean by cluster? Heavy cluster means what? I have to have a little calculation to tell me what is heavy, but this is what is the overall heuristic. Here is what I do. That is my graph. Select a node with the maximum sum of NB incident edge weight. What is NB is 3, means that I use 3 bits to encode this. So, what you are saying is you select a node with the maximum sum of 3 incident edge weights. Why 3 we can decide later, but it is like this. Over here you would select B, that is my prioritization. Okay. Why B? Because if you add the 3 heaviest edges that are connected to it, it would be 4 plus 6 plus 2. That 4 actually is not there. So, these 3 states, these 3 edges. Okay, the fourth one is 0, so that does not count, the other 3 count. So, that is my heaviest node. So, I select that node n and you assign some code to it, does not matter, as we said the absolute value does not matter. So, let us just assign all zeros, 0 0 0 is the code for B. That is not important, but what is important is what we are doing next. In the choice of these 3 connected nodes, they are the heaviest ones that are connected to B. Heaviest means in terms of their relationship with B, that is heaviest. So, we can satisfy those 3 relationships at least by assigning codes to A, D and E, those 3 nodes that are minimally distant from B. That much at least we are able to. As you can see, this is not guaranteeing optimality, but is a nice heuristic in the sense that you are selecting. How did you select B? Probably because among the edges that are there, those are the heavy ones that you managed to select, and this informally is the cluster that we are talking about. Now, you see why it is NB, why the heaviest 3 edge weights as opposed to the cluster which could also be the sum of all the edges that are connected.
That's why.
Why not sum of all the edges? Why did I say 3 edges?
Because the heaviest weight node is connected to 3, that is why you chose 3.
Because the flexibility of giving unidistant codes is there only for 3 others, right? You do not have that flexibility for the 4th. So, that is the reason for the heuristic. Yeah. You could also have chosen the 4th one, but then you would again have to prioritize. The 4th one you would not be able to give a distance of 1, you would have to select something else. So, but this is the reason for the choice. Okay. After that I just remove B from the graph and I just repeat the first step. It is a simple heuristic. Start with this. The choice of that node means actually in the process I have done most of the encoding. Not only have I chosen the encoding for B, but I have also chosen the encodings for A, D and E, but I remove only B from the graph and continue, knowing that for part of the graph the encoding is already done. Okay. Now, for the remaining nodes that are there, I will go through the same process, which means that A is selected here. as my heaviest node because of the sum of still NB here. So, sum of these 3. As it turns out, 2 of its neighbors are already encoded, nothing to do for them, and I choose for C the minimally distant encoding from A that is still available, not yet used. Right. So, these 2 are already taken up, you can't use that, but whatever else is available among those you can choose one that is minimal. So, if you want to find other encodings that are at a distance of 1, you could invert this one, and as it happens that is available, or even this one you could invert. So, such an encoding can be chosen for C. That is essentially this embedding strategy. So, conceptually what we did is, in a first stage we looked for patterns and built a graph. Why go through those 2 stages? It simplifies the formalism somehow. Particularly the second part is totally unrelated to the first one. It is assuming that you did a good job in prioritizing those, computing those edge weights. So that the second part is totally decoupled. You could use a simple or a complex, whatever kind of algorithm you want, and those are the 2 conceptual stages. There is not much contribution in the second stage, except that we reuse one of the known solutions, but the contribution as usual in these synthesis problems is in a good modeling of your particular problem into a graph problem, so that we can use some existing solution. So, the quantifying of those edge weights is really what is happening in this algorithm.